Hi, during this session I will be considering the impact on magnetic forces on moving charges. For instance, if we consider an electron, as it travels through a magnetic field, we often see it taking on a helical motion through the field. And actually what happens when this takes place in the Earth's atmosphere, we get a release of something called Bremsstrahlung radiation, which is a release of radiation as electrons travel through the radiation. So that's a very specific, we're going to keep it at a very general level. So let's just think about this as from a starting point. Okay. If we accept that a charged particle feels a force when it moves through a magnetic field. This kind of makes sense because we've already taken on board the fact that when current is traveling through a wire, that undergoes a force. So if we simplified it and just thought about it, that current being consisting of one electron moving, then it would make sense that there'd be a force on that one electron or one charged particle. So what forces do you think would have an impact to the size of this force? Well, if we think about a wire, some of the features when we look at a wire are, first of all, the magnetic field strength. That would make a lot of sense. The amount of current traveling through, so that would have an impact on either the amount of charge or the rate which the charge was traveling, so the speed or the velocity. Now I'm going to identify those into a formula quite soon, but to start off with I'm going to introduce it through a little bit of deriving. So I'm going to try and derive the formula which gives us the values for the size of the force, and hopefully it'll help you with your understanding. So let's start off by thinking about a wire and then redefining current. So if I recognize that current is the amount of charge passing through a wire per second over a unit of time. Now if I think about this in a little bit more detail, and now I look at the amount of charge which is in a certain part of the wire, I recognize that if I know the area and the length of the wire which contains the charge which is passing through at that moment, and I know the charge density, this is going to be n, in this case the electron density, then it means I can work out exactly how much charge is in that zone, so the zone that's going to pass through in 1 second. If I think about this a little bit further, I can recognize that dividing the length travelled by the time actually gives me the velocity. And in the case of electricity, this would be known as the drift velocity. So the velocity of the electrons travelling through the conductor. So here I've got current equals the electron density times the area multiplied by the velocity times by the charge on an electron. So that's my starting point. What I'm going to do is combine that value with the fact that we know force equals to Bill, magnetic field strength times the current times the length of a wire. So this is what we've worked out for the impact on a wire. I'm now going to replace what I've just worked out for current. The one switch I've done is I've placed Q in there rather than E, just to show that it's the amount of charge. Now if I multiply this through, I've got NaL density, area, length times the magnetic field strength times the charge times the velocity is equal to the force. Now as NaL is basically the density times the volume, it actually tells me the number of particles. So if I'm only interested in the force on each individual particle, I divide this value by NaL, which cancels out to give me the force equals the charge times the velocity times the magnetic field strength. So that's the force this is going to undergo. Any charged particle is going to undergo. Explicitly, so let's think about the units again. This happens when charged particles moving at 90 degrees to the field. So that means that there's no issues with angle. So then I've got my force measured in newtons equals my flux density measured in Teslas multiplied by my charge in coulombs multiplied by the velocity in meters per second. And that gives me force equals B times Q times V. Now remember, if the charged particle happens to be moving at 90 degrees to the field, we've got to take into consideration of that, similar to the manner which we took into consideration with the wire and it not being parallel to the magnetic field, and we just add a feature which is sine theta, and theta is the angle between the motion of the particle and the magnetic field. So now I've got a formula which is kind of useful. Now earlier on we've been talking about magnetic fields as well as force. Is really useful to work about direction, and this is one of those little tricks that you've got to think about quite carefully, because if we think back to Fleming's left-hand rule considered the flow of current, and that's the conventional flow of current. So that's actually not the direction that your electrons are flowing in. So let's think about this carefully, and a few spots just to help you work this through. If we consider which direction the force is going to act, the force is always at 90 degrees to both the current and the field, using Fleming's left-hand rule. But as this is conventional current, what we have to think about is, for a negative charge moving to the right, it has to be treated as a positive charge moving to the left. Okay. And so if we point our middle finger in the opposite direction to the movement of the negative charge, that gives us the direction which we want to be thinking in. So you've just got to remember to swap the direction of how you imagine current to be flowing and the direction of a negative charge. And with a positive charge, it will carry on going in the same direction as the conventional current, vice versa. So that's the one little trick. The fact it's always travelling at right angles means that this very quickly becomes related to circular motion. Because what happens is, if we have an electron travelling through a magnetic field, what happens is that the force it undergoes is likely to be at right angles to both the velocity, the direction, and the magnetic field. And this sets up a situation where we very quickly get a centripetal force. So quite often you'll have questions which consider this. So let's think it from the basics. We know from Newton's second law, F equals ma. If we're thinking about circular motion, the mass is the same and the acceleration will be described as v squared divided by r. And in this case, the force caused by a charge moving through a magnetic field we've just worked out is QVB, assuming it's 90 degrees, so we're keeping it simpler for this stage. With that information, depending what we're given, we can work a few things out, but quite quickly we've got to remember that we can cancel one of the velocities. So we've got QB equals mv divided by r, v being the velocity. And for instance, I could rearrange this, and if I knew the mass of the particle, the velocity of the particle, the magnetic field strength and the charge, I could work out the radius of the circular motion it would undertake. So with that in mind, let's just think about one final question. A proton of mass 1.6 times 10 to the minus 27 kilograms and a charge of 1.6 times 10 to the minus 19 coulombs moves in a circular radius of 21 centimeters perpendicular to the magnet field of 4,000 Gauss or 0.4 Tesla, which is the important bit. Find the period of the motion and the speed of the motion. Okay. So these two things are intertwined, both the period and the speed. So we start off by recognizing that we know that QVB equals mv squared over r. From this we can work out that the velocity is going to be 8.05 times 10 to the 6 meters per second, just by rearranging that and substituting the right values. Then I've also got to remember that the period is actually going to be the distance travelled divided by the speed. Is going to tell me that the distance travelled for one circle divided by the speed is going to give me the period, and that gives me a value of 1.64 times 10 to the minus 7. So things to remember: The force applied on a charge moving through a magnetic field is calculated through the formula of QVB, and this is quite often interlinked with the ideas of circular motion.